Today we are going to graph rational function. So what do you mean by rational functions? A rational function is any function which can be written as the ratio of two polynomial functions, where the polynomial in the denominator is not equal to 0. But this definition sounds so abstract, so let's do some exploration activity so that we can develop our intuition about what rational functions are. So this is our setup. I have here an old iPad. I have here a graphing calculator where I'm going to show you the transformation of the graph. We'll write our notes here and we'll write the questions that we are solving here. So the first thing that we're going to do is let us compare the graph of f of x equals 1 over x and g of x equals negative 1 over x. The function f of x equals 1 over x is called the parent function of the rational functions because most of the graphs can be derived from these parent functions through several transformations such as sliding or translation, flipping the graph or reflection, enlarging or reducing the graph, or what we call as dilation. So let's begin with the graph of f of x equals 1 over x. You can see here the graph of f of x equals 1 over x. It is a hyperbola with two branches. One is in the first quadrant and the other is in the third quadrant. You will notice that the graph of f of x gets closer and closer to the y-axis, but if you are going to zoom out, you will notice that the blue curve actually does not intersect the axis. The same is true with the x-axis and the curve. The curve gets closer and closer to the x-axis, but the curve does not intersect the x-axis. Now, that line where the graph gets closer and closer to but do not actually intersect is what we call as the asymptote. And there are three types of asymptotes. We have a horizontal asymptote, we have a vertical asymptote, and we have a slant or oblique asymptotes. And we're going to talk about them later. Now, what I want you to notice is the comparison of the graphs of f of x equals 1 over x and g of x equals the negative of the first function. So it's negative 1 over x. What is the difference between these two graphs? So let's put that in our Desmos graphing calculator. So the original graph is the blue graph. It looks like this. And then the second graph is this graph that is now in the second quadrant and in the fourth quadrant. So let me show it again. This is the parent function, f of x equals 1 over x, and this is the second function, g of x equals negative 1 over x. The question is, what happens from the first graph to get the second graph? So to understand what happened to the graph of f of x equals 1 over x and how does it compare with the graph of g of x equals negative 1 over x, I trace here the graph of f of x equals 1 over x. What I'm going to do is I am going to trace that. So it's the same graph, f of x equals 1 over x. To get this g of x equals negative 1 over x, what I'm going to do is I'm going to reflect this, flip over across the x-axis, and the resulting reflection now is the graph of g of x equals negative 1 over x, which is now this graph. So what this means is when you change the sign of the function from positive to negative, physically it resulted to reflection or flipping over the graph of the function. If the graph is like this, you multiply that function by negative 1, the graph will be flipped over the x-axis. Now in the second part, let's do the comparison of these three functions. F of x is the parent function again, 1 over x, and then we have g of x where we added a constant 2 to the parent function, and then we have h of x where we subtracted 3 to the parent function. So let's look at the graph in the Desmos graphing calculator. So that one is the graph of the parent function 1 over x. If we added 2 here, this is the resulting graph. The green one is the resulting graph. What happened? From the original graph, when you add this positive 2, the graph will be translated 2 units up, like that. So from here, we move this 2 units up, so it's like that, which is now the new graph. Similarly, if we subtract 2 from the original function, f of x equals 1 over x, the graph will move 2 units down. That kind of transformation is what we call as translation. You can translate the graph up or down, right or left. And the effect of this number that's added after the parent function is to move the graph up or down depending on the sign. If the sign is positive, we move up. If the sign is negative or we have minus here, we are going to move down. Now this time, the question is, what happens if instead of adding a number after the 1 over x, we add the number next to x? Like from 1 over x, we have 1 over x plus 2 and 1 over x minus 4. What happens to the graph? Let's check again our Desmos graphing calculator. So this one is the original function, f of x equals 1 over x. The next one is when we added positive 2. So let's show it again. The blue one is the graph of f of x equals 1 over x. Then let's graph 1 over x plus 2. So what happens to the graph? The blue one was translated to the left 2 units. So it's like this. You have the original function, you move that 2 units to the left, 1 and 2. That resulting graph is now the graph of 1 over x plus 2. So we just move it to the left. How about the graph of 1 over x minus 4? So let's look at our calculator again. So what happens was, from the parent function, when you subtract 4 to x, the graph is moved 4 units right. 1, 2, 3, 4. So that's what happened to the graph now. This kind of transformation is what we call as a horizontal slide or horizontal translation, whether we translate to the right or to the left. But pay attention to the sign. When you have the operation x plus 2, intuitively some people are thinking it should move to the right. That's wrong. What's going to happen is the graph is going to move to the left when the operation is plus. When the operation is minus, that's when you move to the right. So 1 over x plus 2 compared to f of x equals 1 over x is a translation to the left 2 units. Whereas the graph of the function 1 over x minus 4 is a translation 4 units to the right compared to the parent function 1 over x. These two transformations, the translation to the right or to the left and the reflection vertically or horizontally, are very, very important in order for you to understand the graphing of rational functions in the HK form, where the h and the k are called the asymptotes, the vertical and the horizontal asymptotes. And the graph of the function f of x equals a over x minus h plus k, where a, h, and k are constants, is just a transformation of the mother function f of x equals 1 over x. Specifically, this h says you are going to move h units to the right. This k says you are going to move k units up or down. And when there is a sign here that's negative after a, you are going to flip over the graph. Now at this point, there's one more transformation that we need to do before we can start graphing any rational function. I want you to look at this mother function again. F of x equals 1 over x, and this red curve is the graph. What if instead of 1, I double that, I make it 2? Look at what will happen to the graph here. So you notice that the green curve was added, but it's a little farther away from the point of origin. What if instead of 2, I make it much bigger, this time 3 over x, and that third graph, which is color red, is added. That corresponds to 3 over x. Now let's try 4 over x, 5 over x, 6 over x. So the bigger the number, which corresponds to the a in our formula, this gets farther and farther away. Now this time, let's make it a number between 0 and 1. Instead of multiplying by a number greater than 1, I'm going to multiply by a number less than 1. So this time it's 0.5. And then make it even smaller, 0.4, 0.3, 0.2, 0.1, and so on. And this very, very small one. So what do you notice? There's a pattern. From the mother function 1 over x, if we multiply it by a number greater than 1, the graph becomes bigger and bigger. And if the graph is multiplied by a number between 0 and 1, the graph becomes smaller and smaller and smaller. That is the transformation, which we call as dilation. And dilation has two parts. One is to enlarge, represented by multiplying by a number greater than 1. And the other one is to reduce, that is represented by a scale factor that is between 0 and 1. And so to summarize these three transformations that we talk about, let's review them. One is reflection. So you can think of a mirror. Translation can also be imagined this way. You have a mountain with water below, and you can see the reflection of the mountain below. That's reflection. And then there's also what we call as horizontal reflection, where you reflect the image horizontally across the y-axis. And then there is also what we call as oblique reflection. That happens when the mirror line is oblique or slanting. Then we also talk about dilation. Dilation is a transformation where you can either multiply by a scale factor more than 1 and the effect is to enlarge the image, or you multiply by a scale factor that's between 0 and 1 and the effect is to reduce the size of the image. And the third one was when we slide the image up or down, which we call as the translation. At this point, we are now ready to graph this rational function. Let's say we have the function f of x equals 1 over x minus 3 plus 3. Before we graph it here, let us have some idea of how the graph looks like based on our knowledge of transformation. So we know that the graph of the parent function 1 over x is like this. And the transformation that happens here is we are going to move 3 units to the right. So this one will move 1, 2, 3. So there would be, so the vertical asymptote is at x equals 3 and the horizontal asymptote is at y equals 3. And the graph would be drawn somewhere here and somewhere here. So without actually getting into the specifics, we already have an idea that the graph would look like this because of our knowledge of transformation. So the first thing that we're going to do is check for what value of x will make this denominator be equal to 0. And that x value is our vertical asymptote. So our vertical asymptote would be x equals positive 3. Because at x equals positive 3, the denominator would be 0. Then let's locate now that vertical asymptote, x equals positive 3. And then this constant plus 3 here is our horizontal asymptote. So our horizontal asymptote is y equals positive 3. Let's identify if there is an x and y intercepts. So at x-intercept, y equals 0. At y-intercept, x is 0. So if y is 0, we have here 0 equals 1 over x minus 3 plus 3. Subtracting 3 both sides, we have minus 3 equals 1 over x minus 3. And then multiplying both sides by x minus 3, we got negative 3x plus 9 equals 1. Subtract 9 both sides, negative 3x equals negative 8. So x is positive 8 over 3. So the graph will cross the point x equals 8 over 3 and y is 0, which is our x-intercept. Then for the y-intercept, we let x be 0. So if you let x be 0, we have y equals 1 over 0 minus 3 is negative 3 plus 3. So y equals 3 minus 1/3 is 2 and 2/3 also. So y is 2 and 2/3. And now let's connect those points. Next, let's locate any 2 points here. So let's say locate 6 at x equals 6. What is y? So let's substitute. If x equals 6, we have 1 over, this is 6 minus 3, so that means 3 plus 3. So this is equal to 3 and 1/3. 6 and 3 and 1/3 here. And then let's locate another point, let's say 4. At x equals 4, what is y? So you have 1, 4 minus 3 is 1, so 1 divided by 1 is 1, plus 3, we get 4. So the point 4, 1 is also in the graph. And then we can approximate the graph this way. So what we now have here is the sketch of the graph. F of x equals 1 over x minus 3 plus 3. But as I have said, if you know transformation, in your mind, you can already picture this graph even without doing these computations yet. At least you already have a sketch of the graph in your mind. Rational function, we are interested in its domain and in the end and local behaviors of the graph. So let's do that. So at this point, let's identify now the domain, the range, and the end behavior as well as the local behavior of this function. The domain is the set of all x's such that x is not equal to that number that will make this denominator 0, and that number is 3, which is our vertical asymptote as well. This is written in set builder notation. An equivalent way of writing this in interval notation is to look at the graph. The graph is coming from the left infinity going to x equals 3. So going to 3, but does not touch 3, so it's open interval. That's one branch. The other branch of the graph is starting at 3 and then going to the right without limit. So we write positive infinity. These two are equivalent. One is written in set builder notation, the other is written in interval notation. We already identified the x and the y intercepts. The range is the set of all y's such that y is not equal to this horizontal asymptote, which is equal to 3 as well. And in interval notation, we write from negative infinity up to 3 union. So I'm reading from here, going here, and then starting here again, going up from 3 up to positive infinity. The end behavior is the behavior of the graph at these ends. We have two ends. So what happens to the graph here? As x approaches positive infinity, the function f of x, which is the value of the y, is getting closer and closer to the horizontal asymptote y equals 3. So this also approaching that horizontal asymptote 3. And at the other side, as x approaches negative infinity, that means you are going to the left, going this way, the function also is approaching positive 3. Now, since both of them are approaching the same number, we can write them together as x approaches positive or negative infinity, f of x approaches positive 3. Those are the end behaviors. Now, let's look at the behavior at the local point. That means at the vertical asymptote. So what's the behavior at the vertical asymptote? Notice that as x approaches positive 3 from the right, we write that as x approaches positive 3 from the right. What happened? F of x approaches positive infinity. And the way to write that is, we say the limit of f of x as x approaches 3 from the right is positive infinity. There's still another part here. What happens at the other side? We also said here that the limit of the function f of x as x approaches this point, which is 3, coming from the left, so you put minus here. So the limit of f of x as x approaches 3 from the left is equal to that value where this graph is approaching to. And what is that value? It goes lower and lower here, and that is negative infinity. So these are some of the analysis that we can do about this graph, which is a rational function. And these notations that you are seeing now is the same notation that you will be encountering in your introductory calculus course. Okay, let's have another example. So by just looking at the graph, we can already picture in our mind how does the graph look like. We can start sketching the graph and then we'll just do the precise graphing later on. So what's our analysis? The first thing I do is look at this number 2. That indicates that the vertical asymptote is at x equals positive 2. Then this minus 2 here is our horizontal asymptote. That means there's a line that cross here, which is our asymptote. Then originally, the graph of the parent function is something like this, but notice that you have this negative sign. Because of that, the graph would be reflected, and the effect of that reflection would be the graph would be somewhere here. And then notice that because there's a 3 here, instead of the graph being close to the asymptote like that, it would be a little bit farther away. Instead of the graph being close to the asymptote, it would be a little farther away. So that's our estimate. The graph would be somewhere here, and the graph would be somewhere here. And let's verify that. Okay, so let's do it now in a more precise way. So again, the same asymptotes. X equals positive 2 and y equals negative 2 are the vertical and horizontal asymptotes respectively. So we now say the vertical asymptote is x equals 2. The horizontal asymptote is y equals negative 2. Are there any x and y intercepts? We suspect that there is a y and x intercept because the graph would be crossing this way here. So let's find the x and the y intercept. If you let x be equal to 0, you are computing for the y-intercept. If you let y be equal to 0, you are computing for the x-intercept. So if we let x be 0, we are left with y equals negative 3 over 0 minus 2 is negative 2 minus 2. And this gives us y equals positive 3/2 minus 2, which is equal to negative 1/2. Now for the x-intercept, if you let y be 0, you have 0 equals negative 3 over x minus 2 minus 2. Add positive 2 to eliminate this minus 2, so you have 2 equals negative 3 over x minus 2. And then multiply by x minus 2, you will get 2x minus 4 equals negative 3. And then solving for x, you have 2x equals 1 and x equals 1/2. So the x-intercept is 1/2, we'll cross here, and the y-intercept is negative 1/2. So x-intercept is positive 1/2, the y-intercept is negative 1/2. Then let's trace the graph. So that's our approximate curve. There's another one at the bottom. Now for here, we can just select any arbitrary point. So let's select 5. At x equals 5, what is y equal to? So you'll have negative 3 over 5 minus 2 minus 2. 3, negative 3, 5 minus 2 is 3 is, so you get here negative 1 minus 2 equals negative 3. So you have 5 and negative 3. And then let's try x equals positive 3. If x equals positive 3, you have negative 3 over 3 minus 2 equals minus 2. So you have negative 3 over, this is 1 minus 2, so you get negative 5. 3y is negative 5. So this 3 and negative 5. What do you notice? From the intersection of the vertical and horizontal asymptotes, if I count 3 units to the right, 1, 2, 3, I go down 1. From here, I count 3 units going down, 1, 2, 3, and then I go right 1. That is indicated by this positive 3. So that would now be the sketch of our graph. Then let's analyze the behavior and the domain of this function. So what is the domain? The domain is the set of all x's such that x is not equal to positive 2, because at x equals positive 2, the denominator is 0. And what is the range? The range is the set of all y's such that y is not equal to negative 2. And then we already computed the x and the y intercepts. The x-intercept was x equals 1/2, and the y-intercept was y equals negative 1/2. And then let's analyze the behavior of the graph. So for the local behavior at the vertical asymptote, we now say that the limit of the function f of x as x approaches that vertical asymptote 2 from the right is equal to, so you're coming from the right, going this way, it's going to negative infinity. And the limit of the same function f of x as x approaches 2 from the left, so you're approaching 2 from the left, you're coming to this number 2, and y is going up, going to positive infinity. And then for our end behavior, we look at the behavior here. As x approaches positive and negative infinity, f of x approaches this horizontal asymptote y equals negative 2. So far this is our analysis for this rational function. Let's go to the next one. Now, before we graph the next set of functions, it is very important that we know the rule for finding the horizontal asymptote. There are 3 cases to find the horizontal asymptotes. To find the horizontal asymptote, we compare the degree of the numerator and the degree of the denominator. So, what do you mean by the degree of the numerator? If you have, let's say, 2x cubed over 2x squared, the degree is this highest exponent in the numerator, and the degree is the highest exponent in the denominator when written in the standard form. We now say that the degree of the numerator here is degree 3, and the degree of the denominator is degree 2 or second degree. So these are the rules. If the degree of the numerator is less than the degree of the denominator, for example, if you have 1 over x, the bottom is first degree, the top is 0 degree because there is no variable. If this is the case, the horizontal asymptote is the x-axis itself, which means y is equal to 0. That's the first case. When the degree are equal, for example, you have 2x to the third over, let's say, 3x to the third, when these two exponents are the same, then The horizontal asymptote is the line determined by this coefficient. We just get y equals whatever is the ratio of their coefficients, 2/3. So again, when the exponents are the same, so again, when the degree of the numerator and the degree of the denominator are the same, meaning the highest exponents are the same, then the horizontal asymptote is just the ratio of their respective coefficients. When the degree of the numerator is greater than the degree of the denominator, as in this case, you have 3 greater than 2, then there is no horizontal asymptote. Instead, what we have is what we call as the oblique or slant asymptote. For any rational function, you can have multiple vertical asymptotes, but you can only have one horizontal asymptote or one oblique asymptote. But when you have a horizontal asymptote, there's no oblique asymptote. When you have an oblique asymptote, there is no horizontal asymptote. So those are some of the guidelines that we have to keep in mind when we are dealing with horizontal asymptotes. With that knowledge of the horizontal asymptote, we are now ready to graph function number 3. So notice that here, you no longer have that x minus something form. You have x squared and you don't have the k value here. So in this case, what we're going to do is we're going to factor out the numerator and the denominator if it can be factored out. So let's factor them out. The numerator is a difference of two squares which can be factored as x plus 2 times x minus 2. You can review your factoring if you are confused here. Now the denominator is a difference of two squares also, and its factors are x plus 3 times x minus 3. Now from here, you notice that there would be two vertical asymptotes because there are two values of x that will make the denominator equal to 0. The first is the root of this factor x minus 3, so x equals negative 3. And the other is the root of this, which is x equals positive 3. So you get the opposite sign of this number. So look at x equals negative 3. That is one of the asymptotes, vertical asymptotes. And then positive 3. Now for the horizontal asymptote, notice that the degree of the numerator and the degree of the denominator are equal. So what you're going to do is just get the ratio of their respective numerical coefficients. So you have the ratio 1 divided by 1, which is equal to 1. This represents now the horizontal asymptote. Now this is x squared. So we expect a graph like a praying hand, somewhere like going this way. But because there is an x squared minus 9 here, that graph would be split. One here, you will have one graph here and one graph here, and something like somewhere like that. But let's identify the exact points. So what we are going to do next now is identify the intercepts. So now let's check if there is an x and y intercept. So for the x-intercept, y equals 0. For the y-intercept, x equals 0. So if you let y be 0, so you have 0 equals x squared minus 4 over x squared minus 9. And then multiply both sides by the denominator, you get 0 equals x squared minus 4. So this means that 0 equals x plus 2, x minus 2. And split the 2, so x equals negative 2 or x equals positive 2. So the graph will cross these 2 points. For the y-intercept, we let x to be equal to 0. So if you let x be equal to 0, you have y equals 0 minus 4, so negative 4, over 0 minus 9, so you got positive 4 over 9. Positive 4 over 9 is somewhere here. It's less than 1/2. So that would now be the first part of the graph. Then let's identify the graph here and the graph here. Now the remaining graph would be a graph somewhere here. So what you can do is just assign value for x and compute for y to verify these points. So this one now would be the graph of f of x equals x squared minus 4 over x squared minus 9. Now let's do the analysis of the behavior and the domain of the graph. So let's analyze now the domain. I would like to write this in interval notation because the interval notation will give us an idea of what really are the intervals of the domain. So from negative infinity going to negative 3, union from negative 3 to positive 3, union from 3 going to positive infinity. So that's our domain. Now for the range, in more complicated function, it's hard to find the range unless you compute for the inverse function, because notice there's a gap here and you need to find what is the vertex of this curve. For now, let's skip the range. And then the intercepts we already computed. So the y-intercept was 4/9 and the x-intercept was 2 and -2. What is the end behavior? As you go to this right end, as x approaches positive infinity, f of x approaches the horizontal asymptote y equals 1. The same can be said about the behavior at the left, so we can just write this as 1. As x approaches positive or negative infinity, f of x approaches positive 1. And then here there are 4 behaviors. The limit of f of x as x approaches this vertical asymptote, which is -3 from the left, is positive infinity, and the limit of the function as x approaches -3 from the right, so from the right approaching -3 is going this way, that is -infinity. On the other side, the limit of f of x as x approaches 3 from the left, so as you go to positive 3 from the left, the graph is going down to -infinity. And finally, the limit of f of x as x approaches positive 3 from the right, so from the right going to positive 3, the graph is going up, that is positive infinity or simply infinity. So those are the behavior of the graphs. Now let's try this other example, because this will illustrate when there is a hole in the graph. So the first thing that we have to do is try to factor out the numerator and the denominator. So let's do that. F of x is equal to, what are the factors? There's a common factor here of 2, so we can write as 2 times x squared minus 6x plus 8. And then factoring this further, we can factor as x and x. 8 could be -4 minus 2. So the factors of the numerators are 2 times x minus 4 times x minus 2. And then let's factor the denominator. So you have x squared minus x minus 12, which can be factored as x and x. You have -12 to get and -4, positive 3. So you have x minus 4, x plus 3. Now what will happen here is we will be able to cancel out one of the factors. We'll be able to cancel out this x minus 4 and x minus 4. If there is some factors that you can cancel out, that will result into a hole instead of an asymptote. And finally, the simplified form is 2 times x minus 2 over x plus 3. And from here, our vertical asymptote is x equals -3. So we have a vertical asymptote at x equals -3 and a hole in the graph at x equals 4, because here you have x minus 4. The root of this factor is x equals 4. But since we are able to cancel that out, instead of having a vertical asymptote, we have a hole at x equals 4, and then we'll compute whatever is the y. So if you substitute this 4 in here, in the simplified form here, you will get 2 times this 4, so 4 minus 2, that becomes positive 2, over 4 plus 3, which is 7, and that gives us 4/7. So the whole is at the ordered pair, x equals 4, y is 4/7. 4/7, somewhere here, there is a hole in the graph. So let's continue. We have one vertical asymptote and we have one hole. What is the horizontal asymptote? The horizontal asymptote would be determined by the degree of the numerator and the denominator. Since the degree of the numerator is 2 and the degree of the denominator is 2, then the horizontal asymptote is the ratio of the respective coefficients. So you have 2/1, which is equal to 2. So we have a horizontal asymptote at y equals 2. Then let's find the y-intercept. At the y-intercept, x equals 0. If x equals 0, the numerator would become 16. So because this becomes 0, 0, so you have 16. And the denominator would be, this becomes 0, 0, -12. And 16 over -12 is -4/3, or -1 1/3. So the graph is going to cross here. So the shape of the graph would be like that. And then there's a break because there's a hole, and then it continues like that. And the other point would be on the other side. So we just assign values for x and compute for the y somewhere here. We know that if the distance is this much, the distance also from here to there is around the same. So this is now the graph of this function. What makes this example different than the previous one was the presence of this whole. The whole happens when, after factoring the numerator and the denominator, you found that there are factors that can be cancelled out. The roots of those factors that can be cancelled out is the x-coordinate of the whole. Once you find that x-coordinate of the whole, substitute that in the simplified form of the numerator and the denominator after doing the cancellation, and then you will be able to find the y value of the whole. So at this point, what we are going to do is identify the domain and the range. So what is the domain? The domain would be from negative infinity going to negative 3, union from negative 3 going to 4, union, and from 4, open interval, going to positive infinity. And then what's the end behavior? The end behavior is as x approaches positive infinity, f of x approaches the horizontal asymptote y equals 2. The same is true when you go to the other side, so this becomes plus or minus infinity. And then the behavior at the vertical asymptote, the limit of f of x as x approaches negative 3 from the left is positive infinity. The limit of f of x as x approaches negative 3 from the right is negative infinity. And of course, the vertical asymptote is x equals negative 3. The horizontal asymptote is y equals positive 2.